In this second video on co-adjoint orbit quantization, we'll discuss again a particle on an orbit of SU2, and SU2 will be our prime example for illustrating orbit quantization. So to define the particle action, we take a representative of the Lie algebra of SU2, and we consider a map G from the world line of the particle into the group manifold SU2. We can then define a particle action, which equals J plus a half integral over the world line d tau of the killing metric evaluated on lambda and G minus 1 time derivative of G, where we assume that the map is from tau to G of tau, where tau parametrizes the world line. One can think of the brackets as a trace. J plus a half is quantized in half integer units. So now what are the symmetries of this action? There is a global symmetry, which is to multiply G by hg, where h is an element of the group, in this case SU2. This clearly leaves the action invariant. And then secondly, there's a local symmetry, which multiplies G by gh of tau, where h is an element of the commutant of lambda. So if h of tau commutes with lambda, then the action will change by a total derivative, and this is a symmetry of the action, which is a gauge symmetry. In the case of SU2, the gauge symmetry is a U1 symmetry, and it reduces the phase space from an SU2 phase space to an SU2 module 1 phase space. The variation of the action will give rise to the equations of motion. So if we think of G minus 1 delta G as a generic Lie algebra valued variation of the field G, then we will find that the equations of motion are nothing but lambda has to commute with G minus 1 d tau G. These are the equations of motion, and it's a small exercise to prove it. The global symmetry of the action by the Noether procedure will give rise to conserved charges. These are I equal to G lambda G minus 1. We can project these charges onto any Lie algebra direction, and therefore, for instance, for SU2, we will have 3 charges. These 3 charges will satisfy an algebra, which is nothing but the algebra G, namely the algebra of the global symmetry. Another exercise is to show that these charges are indeed conserved using the equations of motion. All of this is in a slightly abstract mathematical notation, so for SU2 we can make this all more concrete by introducing Euler angles, for instance, and writing that a group element is equal to exponential I by sigma 3 over 2. These are Euler angles phi, theta, and psi, and we have Pauli matrices sigma 2 and sigma 3. If we parametrize our group element like this, and we parametrize our Lie algebra representative as being proportional to sigma 3, then we can explicitly compute the action as a function of the time-dependent functions phi, theta, and psi. This will give rise to the action m integral over L d tau cosine theta phi dot, where the dot indicates time derivative. One can then compute canonical conjugate momenta, compute the charges, all explicitly, compute their Poisson brackets, etc., and prove all of the properties that have been abstractly derived above. We saw in a previous video that the quantization of the system is equal to an irreducible representation of SU2. We can in this exactly solvable system, we can prove this by computing, for instance, the character of SU2 by inserting an operator in the path integral with this action. The character of a representation is a trace, and since we have a trace, we'll take our world line to be a circle, and we'll take the circle to have a time length t. Then the operator we wish to insert in this trace is e to the minus im cosine theta t. With this extra insertion, our new particle plus operator action will be m integral d tau from 0 to t cosine theta times phi dot minus 1. To compute the path integral, which basically equals integral d cosine theta d phi e to the is particle plus operator insertion, we change variables and we introduce an eta of tau, which is cosine theta of tau, which is an element from -1 to 1. We will integrate over phi of tau having an infinite range, but we will allow that our initial value of phi is the final value of phi, since we take a trace, plus 2 pi w, where w is an element of z, in order to compactify the direction phi. Since each winding sector is a separate topological sector, we will add a phase e to the 2 pi I alpha times the label of the topological sector w to each sector w. So because this is a periodic path integral, it is equal to a trace of the operator that we inserted, and it is not too difficult to show that this path integral equals the sum over topological sectors, then an integral over the zero mode of eta, let's call it eta naught, then e to the 2 pi I m eta naught plus alpha times w minus I m eta naught t from the operator insertion. The sum over w gives rise to a delta function. So we're going to integrate a delta function over eta naught. And the delta function is one of m eta naught plus alpha minus some integer k. So whenever m eta naught plus alpha is equal to an integer, we get a contribution. And then e to the minus I m eta naught t. For m an integer and alpha somewhere between 0 and 1, this will be equal to e to the I alpha t minus I over 2t times sine mt over sine t over 2. And for m strictly half integer, this will be equal to e to the I alpha t sine mt again over sine t over 2. Now, let's recall that m is equal to j plus a half, where j is the spin of the SU2 representation. So let's also recall that the character of an SU2 representation is the ratio of signs that we have above. And therefore, when m is an integer strictly, j is a half integer. So the first case is when j is a half integer. And we have fermions. So for fermions, we can choose alpha to be a half, and then we get, for this trace, the character of an SU2 representation. If j is integer, we get bosons, and we can choose alpha equal to 0 in order to get the character of an SU2 representation. So we have sketched how to really quantize a co-adjoint orbit in the case of SU2 using a path integral quantization and how to compute the character of the SU2 representation that the quantization gives rise to. One point of this exercise is that this generalizes to at least all compact group representations and in fact to many other cases.